All right, people, this video is on electric fields, okay? And I'm going to be talking about electric field lines. I'm going to be talking about charges. I'm going to be talking about magnets even. So this is a video on electric fields, okay? And funny, I'm going to just start this video with this magnet. Now this is a magnet. And this is the north end and this is the south end. I'm assuming that you can see that. And when we draw magnetic fields emanating from a magnet, right, we draw them coming from the north, right, coming from the north end and going into the south end, all right? That's how we draw them. And the thing's a total loop. Here's an example. Look at this compass. See how it's pointing sort of sideways right there? That means the electric field is that way. And we'll move the compass over here. That means right here the electric field is this way. I can move the compass right here. The electric field is this way. I can move the compass right here. Electric field is that way. See, the compass is always part of the is always pointing where the magnetic field is, okay? And we could go over here and we could connect some lines like this. And check out the compass when it's down here. It's sideways, isn't it? So if you connect all this, you see that, boom, this is what the magnetic field looks like. You know, Mr. Perkins, this video is clearly supposed to be on electric fields. Well, guess what? Electricity and magnetism are super similar. They're the yin and the yang of nature. Electricity creates magnetism, and magnetism creates electricity, right? So you should be familiar with this magnetic field already from class. And let me pause this. We have a little better angle there. So this is a magnetic field I've drawn. The magnetic field emanates from the north end of a magnet and goes into the south end of a magnet. Well, let's talk about an electric field. Here is the charge. This is a positive charge, and you can just think of that as a proton. And electric fields go into free space around charged objects. Electric fields go away from positive objects. And we are said to draw the electric field in the direction a positive charge would move. If you put a positive charge near this positive charge, it's going to move away, isn't it? We draw electric fields 90 degrees to the surface of a charged object and in the direction that a positive charge would move. You may say, Mr. Perkins, that doesn't make any sense because when we think about electricity, it's electrons that are moving and they're negatively charged. I would say that I agree with you and that these rules were drawn before we knew what, were created before we knew what electrons were, okay? So here's some electric field lines right here. They go towards a negative and away from a positive. So you can think of a positive charge as sort of being like the north end of a magnet and a negative charge as being sort of like the south end of a magnet. And when I add more charges here, you end up with more arrows, okay? And if I have more positive charges here, you draw more arrows going away from the positive charge, all right? Now, let's talk about these positive charges. You know, they're kind of, the positive and negative charges, they're kind of similar here to our magnet. And what I mean by that is, look, when you get close to the pole of this magnet, look how many arrows are crammed into this area. Look at the density of the magnetic field. And look at near the South Pole. Look how dense the pole is. You have all the arrows coming together in the space. So there's a really strong magnetic field here, and all the arrows going out of this space give you a really strong, dense magnetic field here. Well, if we look at charges, check this out. When you start to get close, when you're in here close to a charge, look. Look how dense the magnetic field is here. Look, I can make a line that's this long, right here, boom, and cross 3 arrows. But if I drew these lines way out here and I made a line that long, I'm only crossing one arrow. Does that make sense? So the closer you are to the charge, the more dense and the more concentrated and the greater the magnitude of the force exerted by this charge. The closer you get to the charged object, the more dense the electric field is. And you know what? That kind of works like something. Look at these guys. If the air is going out of a positive charge and it's going into a negative charge, then these two objects will be attracted to each other. And we know very simply that opposites attract. Just like the north and south end of magnets, positive and negative charges attract each other, okay? So if we think about having a charge right here, right? We can think about having a whole lot of charge. If we think about having another charge right here, we can think about having a whole lot of charge. And if you have enough electrons or enough protons, you can have what's called an entire Coulomb. 1 Coulomb. A Coulomb is a unit of charge, and it's, if we were talking about electrons or protons, it's billions and billions of them create 1 Coulomb. There's some math we could do here. And I could tell you how many electrons were in a Coulomb. Well, let's do it. Look, I've got some physics reference tables here. And if you look, the elementary charge of an electron is 1.6 times 10 to the negative 19th coulombs, all right? So 1 electron has the charge that's very small. It's 1.6 times 10 to the negative 19th coulombs. So if we wanted to know how many electrons are in a coulomb, we could say 1 divided by 1.6 times 10 to the negative 19th. And that would tell you how many electrons were in a coulomb. I take my calculator and I would say 1 divided by 1.6 EE19 negative equals, and there are 6.25 times 10 to the 18th electrons in 1 coulomb. All right? Now you can think about this in two different ways. Wow, that's a whole bunch of electrons, or wow, that's not many electrons, because electrons are tiny. But this is like, 6.25 billion electrons, right? Which is really not that many when we're thinking about electrons. But anyway, when we have this many electrons or protons in one space, we just call that a Coulomb of charge. Now we've got that out of the way. Now these two right here, these two would be attracted to each other, right? And they would be attracted to each other through free space. So this should make you think of something. We've got something over here, like a planet, and something else over here, and they're attracted. Yeah, it should make you think of gravity. Except for gravity operates by this one being massive, and this one being massive, and then warping space-time, and then coming together. So when we think about gravity, the kilograms are important. Well, when we think about electrical forces, it's the charge that's important. Check this out. Isn't this the old formula for gravity? The force in newtons is equal to the gravitational constant times the mass of one planet times the mass of the other planet, or an object, whatever, divided by the distance between them squared, right? Well, when we talk about charges, the force of electricity is equal to K times the charge here, Q1, we call it Q, and the charge here divided by, guess what? The distance between them squared. This is nature. Nature repeats itself. The formula for each of these for gravity and for electrical attraction is the same formula. But check this out. Gravity is super, super weak. The G for gravity is 6.67 times 10 to the negative 11th. And it's just a number. The K in here in the electrical equation, that is 9 times 10 to the 9th. That shows you how many times stronger electrical attraction is than gravity. And if you're like, well, gravity is huge because we're stuck to the earth and stuff like that, I would say this. If you have a refrigerator and you have a piece of paper on it, the earth is trying to pull that thing to the ground, right? And you can put one tiny little 5-cent magnet and stick it to the fridge and it won't fall. So electromagnetism is far, far stronger than gravity. Now let's get back to this. Let's do some math here. Look at these two guys right here. If we had a Coulomb of charge here and a Coulomb of charge here, and we knew how far apart they were, like say they were 20 centimeters apart, right? See this? That's how far apart they are? About 20 centimeters. Then we could calculate the force in newtons that these two would be attracted to each other. And let me tell you something, you're going to be surprised. Electrical force is crazy strong. Let's do the formula. The force between them is equal to K, Q1, Q2 over R squared, all right? So the force of electricity between them, and it's going to be in newtons, is equal to 9 times 10 to the 9th times, this is 1 Coulomb, 1 Coulomb times, this is 1 Coulomb, 1 Coulomb divided by, this is 20 centimeters, so 0.2 meters squared. So this formula I just put to here, this is called Coulomb's law, all right? This formula is called Coulomb's law. We do the math here. We could say 9EE9 times 1 divided by, parentheses, 0.2 squared, close parentheses, equals 2.25 times 10 to the 11th newtons. Think about that. That is a huge number. That's 22.5 billion newtons of force would attract these two. 22.5 billion newtons. If you were standing between these charges would go through you and turn you to butter. What would happen if we had charges that weren't attracted to each other? Well, what if we had a formula like this? What if we had some charge here? And I'm going to give this like a small number, like 0.007 Coulomb, positive charge, all right? So this is a smaller charge. And then we had another charge here. Put some charges in there. We'll call this 0.00009 coulombs, all right? Positive charge. Let's draw the electric field lines going out into space away from these guys. Okay? Now, if we're drawing electric field lines, which you will be asked to do, something should immediately start to occur to you. If this guy's going that way and this guy's going that way, then guess what? We have to, these two guys are going to turn away from each other. Any of the arrows coming out, because guess what? Like charges repel, don't they? So these two guys are pushing apart. Like if you had two magnets turn the wrong way, don't they push apart? Same thing with charges. Let's calculate how hard these things would push apart. It's easy to do. Well, up here in the corner we'll say, okay, we've got Coulomb's law. The force between these two electrical charges is equal to K times 0.007 times 0.0009 over R squared, all right? The distance between these, we could say, okay, I'm just going to measure from the middle. We really should be measuring to the surface. We're going to say these are 11 centimeters apart, so 0.11 meters squared. Put that in our calculator. 9EE9 times 0.007 times 0.0009 divided by parentheses 0.11 squared, close parentheses, equals. All right. Let's change that to scientific notation to make it easier to write. 4.69 times 10 to the sixth. 4.69 times 10 to the sixth newtons. Holy cow, that's still crazy charge, isn't it? That's like 4.7 million newtons. So electrical force is super duper strong. And the formula looks just like the formula for gravity. Instead of mass, the important thing is the charge, and the charge is measured in coulombs. Opposites attract, like charges repel. These charges are very similar to thinking about, the lines on the charge are very similar to thinking about the magnetic field lines. They emanate from the north, or they emanate from a positive charge, and they go to a south, and they go to a negative charge. And the last thing to remember is that electrical charge is super duper powerful and strong.